So what we're talking about is essentially just how we combine functions. Is what we're doing. So let's work with some functions that we're going to keep around. Let's say we have f of x equals the square root of x, and g of x is x squared. So a lot of this section, it's notation. It's just knowing what these things stand for. So when you see this, what it means is f of x plus g of x, and in practical terms, square root x plus x squared. And so that's it. Now, the thing you want to kind of keep in mind is domain. For example, g of x is x squared. Its domain is all real numbers. But f of x is square root of x. Its domain is, well, just the positive real numbers and 0. So now this new function, even though this part of it can take any number you put in there, this one has a restriction. So this is going to restrict the entire function. So the domain for this is, it's going to be restricted by that. So that's just something to keep in mind. Now let's take a look at this one. So that's all it means. We're just going to subtract the two functions. And so again, using our examples, square root x minus x squared from before, and that's what we have right now. So any questions about that? All right. So let's say we have this. This means we're going to take f of x and multiply it to g of x. So again, in practical terms, we'll take square root of x and we multiply it to x squared. So, I mean, you could say that. That would work. Usually you might see it written like this, x squared square root x. And the reason for putting the x squared in front, and the reason we can actually do that is, remember, multiplication is commutative. The order doesn't matter. It's not to confuse anyone who might, if you're writing this out really quickly, you might accidentally make this too long and make it look like it's x times x squared, and the square root goes all the way. That's an easy mistake to make if you're going really fast. So one way to prevent that mistake is when you have a square root or any kind of root, it's multiplied to something else, put that something else in front. Now, another thing you can do with this, though, remember, x square root of x is x to the 1/2. So instead of square root x, we can have x to the 1/2. And since these have the same base, we can just add the exponents. And 2 plus 1/2 is x to the 5/2. So you could put this as your answer also. Any questions about that? All right. Now, you might see something like this. So what this means is f divided by g. And when we have this, practically speaking, this is square root x over x squared And again, you could simplify this if you want. I'm just going to leave it like this for now for the sake of time. So any questions about that? All right. Finally, we could do this. Composition. Now the order here, of course, like these others, it can matter. What this means is that F will take G of X as an input. If we talked about functions as being like factories, you put in some input, you get some output. You can think of F of X as kind of like a mall. It's a huge mall, and G of X is sort of like, it's one of those smoothie stores inside a mall. And so what the smoothie store does is it takes its own inputs and outputs a smoothie, and this all happens inside the mall where you input a smoothie store, and well, we'll see what we get as our output. Hopefully satisfied customers. So that means F is square root of X. So the input's not X, it's G of X. So we're going to do the square root of G of X, or the square root of X squared. So any questions about that? Now you want to be, oh yeah, and this is, of course, if you want to simplify this down, what's the square root of X squared? Well, think back to what the definition of absolute value is. It's the square root of X. Well, one definition, another definition for it is the square root of X squared. And so that can be your answer. So let me do another composition. Compositions are sort of interesting things. Let's see here. So let's say we have something like this. We have f of x is x squared plus x plus 1, and g of x is 5 to the x. Now, I want to find f of g of x. Or put another way, the composition. So what this means is that f composition g of x is going to be f where g of x is going to be the input. So that means we're going to have g of x squared plus g of x plus 1. So instead of having an x squared plus x plus 1, it's g of x squared plus g of x plus 1. Now, g of x is 5 to the x. And then with an exponent on the outside here, the exponents multiply. And that's going to be your answer. So any questions about that? All right. So next up, this is sort of the algebra of these functions. Next up, I want to look at shiftings. So this is where we take these canonical functions and we're actually going to move them around the graph. And this is how we get all the different variations. Well, these are some ways we can get the different variations. So first off, let's take a look at vertical shifts. So for this, I'm going to use a canonical function, y equals the square root of x. And just to kind of bring it back to attention, it looks roughly like this. So that's basically our square root of x. Now, for the vertical shift, if we're going to shift upwards, we're going to take our function and add some constant k. And here, we're going to want k greater than 0. So let me kind of go through why this is going to work. So I'm just going to do a couple values. X is 1 and x is 4. So if we take the square root of 1, and again, this is for y is the square root of x, and this is the positive square root. If it wasn't just the positive square root, you'd see a plus or minus there. So square root of 1, positive square root of 1 is 1, positive square root of 4 is 2. So our graph and we can throw 0 in there too. Square root of 0 is 0. We have this, this, and that. So this is our graph. Now let's take a look at when we add, say, 1 to this. We're going to let k equal 1. So now we got square root of x plus 1. Well, again, so in this case, square root of 0 is 0, plus 1 is going to be 1. It's 0 plus 1. Square root of 1 is 1, but then add that 1, you get 2. Square root of 4 is 2, add that 1, we're going to get 3. So we're going to get this. Pardon me, I'll get that out of the way in just a second there. Get that point. So what this does, by adding 1, this shifts this graph up 1 unit. So that's how you can do your vertical shift. And that just shifts you up. So what if you want to shift down? Well, all you're going to do is subtract k. Or as they put it in the text, and I'll give it to you as they have it in the text, you choose a k that's less than 0 and add that. The idea is that adding a negative is the same as subtracting. So the idea is that if you're adding a negative, so k is a negative number, adding a negative is the same as subtracting. Just to drive that point home is the same as x minus 5. So let's say we do this. Y equals square root of x minus 1, which is the same as y equals square root of x plus negative 1. Same idea. You usually see it as subtraction, but for whatever reasons, the textbook has decided to go with this approach, which is the k less than 0. And we're adding this negative k. But you can just rewrite it as subtraction. That's fine. So let's do our XY chart. So for this one, square root of 0 is 0. Add it to negative 1, negative 1. Square root of 1 is 1. Add it to negative 1. 1 plus negative 1 is 0. Square root of 4 is 2. 2 plus negative 1 is 1. So what does this look like? So we have x is 0, y is negative 1. X is 1, y is 0. And then x is 4, y is 1. So what this does is it shifts y equals square root of x down 1 unit. So that's our downward vertical shift. Questions about that? All right. So now let's take a look at horizontal shifts. So what's going to happen with these? Well, we can have a rightward shift. Now for this, again, we're doing this thing where h is actually a negative number. So I'll show you what this works out to in an example. But for this, let's go to a different canonical function. Let's do this. Y is x squared. And let's consider y equals x minus 1 squared. So this is going to be the same and using the approach from the text. Y equals x plus negative 1 squared. So here's this h. We're adding h that's less than 0. It's negative 1. So what's going to happen here? Well, let's take a look at y equals x squared. So square these x values. We have 4, 1, 0, 1, and 4. So if we graph this, and if you can't see down here, just let me know. So negative 2 and 4, negative 1 and 1, 1 and 1, 2 and 4, and then 0 and 0. So it does something like this. So that's y equals x squared. Now let's consider this one. Y equals x minus 1 squared. So y is going to be x minus 1 squared. So if x is negative 2, we subtract 1, we get negative 3. Negative 3 squared is going to be 9. Now, negative 1 subtract 1 is negative 2. Negative 2 squared is 4. Now with 0, 0 minus 1 is negative 1. Negative 1 squared is 1. And then 1 minus 1 is going to be 0. 0 squared is 0. And then we get 2 minus 1 is 1. 1 squared is 1. So let's see what this looks like. So there's 9 tick marks here, squeezing in. So let's do some graphing. Negative 2 gave us a 9. Negative 1 gave us a 4. 0 gave us 1. 1 gave us 0, and 2 gave us 1. So if we connect these dots, we're going to get something like this. Now I'm going to tack on a couple extra here. So 3 minus 1 is 2. 2 squared is 4. We're still doing x minus 1 quantity squared. 4 minus 1 is 3. 3 squared is 9. So let's take a look at this. This is y equals x squared. This is y, x minus 1 squared. And where you can really see this, look at the vertex. This one, it's at 0. For this one, it's moved to the right 1 unit. So we shifted y equals x squared to the right by 1 unit, or what's going to be our h in this case, or negative plus and negative 1 is what it is. But if you just subtract from x like this, you're going to shift it to the right by that many units. Questions about that? All right. So the next one we're going to look at is shifting leftward. And if I'm erasing too soon, let me know. Now for this one, again, it's f of x plus h. And now h is positive. It'll be greater than 0. So again, we're going to use this one. Except we're going to go with this. So let me make this more consistent. We're going to go to this. Now we've seen what this graph looks like. It has a vertex at the origin. We saw what happens if this is minus 1. It shifts this graph over 1 unit. So let's take a look at x plus 1. So I'm going to do some extra points here. We'll go on like this. So negative 4 plus 1 is negative 3. And square it, you get 9. Negative 3 plus 1 is negative 2. Square that, you get 4. Negative 2 plus 1 is negative 1. Square it, you get 1. Negative 1 plus 1 is 0. Square it, you get 0. And then 0 plus 1 is 1. Square it, you get 1. 1 plus 1 is 2. Square it, you'll get 4. 2 plus 1 is 3. Square that, you'll get 9. And we're not going to need this one. That's going to be good enough. So let's graph it and see what happens. So let's take a look. So for -4, we got 9. For -3, we got 4. -2, we got 1. -1, we get 0. 0, we get 1. 1, we're going to get 4. And then 2, we're going to get 9. So if you think about it, when it's x squared, vertex is here, and it's +1, it's moved over to the left. So there you go. Your leftward shift, you're going to add numbers. If you're going to do a rightward shift, use to subtract numbers, positive integers. All right, any questions? So now for scaling. So this is just moving the graphs around, moving them up and down, right and left. So now we want to kind of modify their shape. We're going to do what's called scale. So first off, we're going to do vertical. So for vertical scaling, we're going to look at a vertical stretch. And this is going to be a number c times f of x, for c greater than 0. So, oh, sorry, greater than 1. So the test function we're going to use, y equals square root of x. And how we're going to stretch it, we're going to multiply by 4. So in this case, c is equal to 4. So what does this do? Well, again, take a look at y equals square root of x. You get 0, 1, 2. Take the square root of each of these x values, you get your y value. So this is your y equals square root of x. So what happens if we scale this by the number 4? Or we're going to vertically stretch it I think this is the reference that the term the text uses is by a factor of 4. So square root of 0 is 0. 0 times 4, 0. Square root of 1 is 1. 1 times 4, 4. Square root of 4 is 2. 2 times 4 is 8. So once again, 0 and 0. Now it's 1 and 4. And then 4 and 8. So the square root, and this is, by the time you get the 4 here on x, your y value is only 2. But here, when you have x value 4, your y value is going to be way up here at 8. So we're stretching this thing vertically. So we're stretching this vertically. We're pulling it up by a factor of 4. So any questions about that? All right. So now we're going to talk about shrinking. So for this one, we'll take 1 over c times f of x. Again, for c greater than 1. Now, c could be a whole number, could be a decimal, but as long as it's bigger than 1, multiplying by 1 over c to f of x is going to shrink it. So again, we're going to take a look at y equals square root of x. I'm going to go with 4. See what this does. So again, xy. So square root of x is 0. 0 times 1/4, still 0. Square root of 1, oh, sorry, not 2, let's go 4. Square root of 1 is 1. 1 times 1/4 is, well, 1/4. And then finally, square root of 4 is going to be 2. 2 times 1/4 is 1/2. So first off, 0, 0. Nothing new. Now this is going to get kind of dicey. At 1, it's 1/4. So let me take a look here. That's a half. That's going to be fourths. So at 1, right there. And then at 4, yikes, we're sort of like that. Now, usually with y equals square root of x, square root of 4 is 2, so we'd usually have our y value up here. This is 1/4 square root of x. Now just to put it in here, usually what we have that's y is square root of x. So what this does, this takes y equals square root of x and shrinks it vertically, shrinks it down. So it's shrunken vertically by a factor of 4. So again, this lets us modify this canonical function into something that we might find more useful depending on what we're studying or trying to model. So that's how you handle things vertically. Now, what about the horizontal? So if you're handling this horizontally, what it's going to be, if we're going to do a stretch, so we're going to pull this thing out like this. It's going to be the reverse of what we do for the vertical. Let me show you what I mean. It'll be f of 1 over c times x, where the 1 over c is on the inside. It's part of the input. And again, for c greater than 1. So again, what we're going to do, we're going to use our square root of x. We're going to do this. Y is square root of 1 over 4x. So if we do our xy chart, so if you put in a 0, 1/4 of 0 is 0, square root of that is still 0. Let x be 1. Well, x times 1/4 is 1/4, square root of 1/4 is 1/2. For 4, 4 times a fourth is 1, square root of 1 is 1. So this is what we're going to get. We're going to need 1/2 in here, so there's a half. So 0 and 0. 1 and 1/2. About there. And 4 and 1. Now, if we go back to y equals x squared, I'm sorry, a square root of x. 0, 0, there's 1 and 1, 4 and 2. So what's happening here, and this can be kind of confusing, is you can say, well, this is just a vertical squish. We're just doing that. But what's technically happening is we're taking this part of the graph and we're stretching it out to here. So technically that's what we're doing. We're taking this little part, this blue part of y equals square root of x, and we're stretching it out over to there. So that's the horizontal stretch. That's what's going on. Have to drop down. So we're taking the part really between 0 and 1, and we're stretching it out so it's between x equals 0 and x equals 4. It's between it's kind of hard to see. I'll read through it. We're going to stretch y equals square root of x. So the part between x equals 0 and x equals 1 is between, we can get rid of this, that's not necessary, is between x equals 0 and x equals 4. So the part that's between here and here has been stretched out to be between here and here. So that's what we're doing with this horizontal stretch. Questions about that? All right. So now we're going to look at doing a shrink. So f of cx for c greater than 1. And again, we'll use square root of x. That's square root of 4x. So xy chart. So 0 times 4 is 0, square root of 0, 0. 1 times 4 is 4, square root of 4 is 2. 4 times 4 is 16, square root of 16 is 4. So what's happening? If we graph this, so what we're going to do, let's graph y equals square root of x. So we have 0, 0, 1 and 1, 4 and 2. We actually have 9 and 3. And then 16 and 4. Let's see, ooh, let me raise that up a little bit. So that's y equals square root of x. Now, y equals square root of 4x. We have 1 and 2. And then we have 4 and 4. So what's going on here? What we're doing is we're taking the graph of y equals square root of x from 0 to 16, and we're squeezing it down between 0 and 4. So to get a y value of 4 for square root of x, you got to put in 16. But now we reach the y value of 4 at 4. So we're just squeezing this in. So that's what we're doing here. We're squeezing it in, taking what's usually y equals square root of x, and we're just squeezing it in between 0 and 4. What used to be between 0 and 16. Questions about that? All right. So the last topic of this section and is just going to be reflection. And the idea of reflection is if we want to turn our graph around across the y-axis or flip it vertically over the x-axis. So the first one we're going to look at is across the x-axis. And what we're going to do is attach a minus sign to f of x. And that's going to be it. So just to show it, again, we'll use our test function, y equals square root of x. And we'll turn this into y equals negative square root of x. So I'm just going to do the xy chart for negative square root of x. I'll put the graph for this on the same graph for that. So square root of 0 is 0, multiply by negative 1, nothing changes. Square root of 1 is 1, multiply by negative 1, you get negative 1. Square root of 4 is 2 times negative 1, negative 2. So 0 and 0, 1 and -1, 4 and -2. And then for y is square root of x, so we've got that. So the result is that we just take y is square root of x and we flip it over the x-axis. All right. Questions about that? All right, one more. So for this next one, we're going to flip over the y-axis. And this is where we place the negative sign on the x. So again, we're going to work with y square root of x. But this time, got a negative in here. We're working with real numbers, so we don't want to be taking the square root of the negatives. So this means this negative has to be canceled out. That means x has to be negative. So that means the domain for this function has to change. So x can be 0 or it can be negative. Negatives and zeros will cancel out this negative, so we're taking the square root of a positive number. So let's see what this looks like. So we've got to use numbers that are less than or equal to 0. So throw in 0, we're going to get 0. Throw in -1, we'll get +1. Throw in -4, we'll get +4, square rooted, we get 2. So let's take a look at square root of x. There, there, there. Now let's take a look at the square root of -x. 0, 0, -1 and 1, -4 and 2. So all this does, barring artistic license, it just takes y square root of x and flips it across the y-axis. that's going to be it. So that's section 1.2. Again, just sort of a review of the algebra of functions. It's a review of the different ways of modifying the canonical functions with vertical shifting, horizontal shifting, vertical stretching, horizontal stretching, and shrinking. And then reflections, flipping across the x-axis, flipping across the y-axis. Combinations of these things are going to let us come up with versions of those canonical functions that might be more useful. We're not just limited to x squared. We can do 3x squared minus 2 and come up with a graph that's more useful to us. So that's going to be something that could be helpful in the future. All right. So I want to move on to 1.3. In section 1.3, we're getting into trigonometry. So this is a review of what you looked at last semester. So the first thing, angles. Now the way we usually construct angles, we have what's called an initial array. Oh, got it on. And then we have what's called a terminal. So the idea is that the angle folds out like that, or rotates out. And so that's our angle theta. It's a measure of how much rotation that we have. Now, there's two ways we measure angles. We measure angles using degrees and radians. Now, degrees are just little wedges. So there's 360 degrees or wedges in one full rotation. So you take a circle, basically divide it up into 360 equal slices, and this is what you're going to get. You're going to measure an angle. So this is 1 degree, 1 degree. This is your angle theta. So what we say is theta will equal 2 degrees. Or we write it, a little degree symbol up there. So that's how we handle degrees. And these 360 slices, these 360 wedges, and the number of wedges that fit inside your angle or inside your rotation, well, that's the measure of that angle or that rotation. The other way of doing this is radians. And here we're going to count how many radii are inside or on the arc length created by our rotation on the J. So it's going to be the radii in the arc length caused by our rotation. If I'm going a bit fast, let me know. So you can think of a rotation in terms of a circle. Let's see, not quite accurate, but this is the center of our circle, and that's going to be the radius. So let's say we have this radius and then another radius right here. And then we have our angle theta. In this case, what theta is the number of radii that are on this arc length created by this rotation or this angle. So here, theta would be equal to 2 radians. Questions about that? Now there's a relationship here. That means theta is arc length of the angle divided by radius. So it's just the arc length. We take this arc length, we divide it by the radius, and that's how we get theta. Now arc length is usually represented by the letter S. So this entire thing is represented by S, and that's the entire arc length. So what this means is that theta is S over R for radius. Usually represent radius with the letter R. If we solve for arc length, we'll get theta times R equals S. For theta in radians. So this is your arc length formula in trigonometry. And theta has to be in radians. It can't be in degrees. You'll get a totally different answer. So questions about that? All right. So we want to talk about conversions between degrees and radians. So let's say you want to go degrees to radians. So what you do is you take degrees and you multiply by pi over 180. And that's going to give you radians. So let me do an example of how that works. So let's say we're going to convert 60 degrees to radians. Well, we take 60 degrees and we multiply by pi over 180. And if we simplify this down, reduce it. And don't forget, Always put your invisible 1 under here if you want. 60 times pi, 1 times 180, 60 pi over 180. Reduce this down, divide top and bottom by 60. That'll reduce it. You're going to get pi over 3. Questions about that? Now, let's say the radians, 2 degrees. Well, what we do here is we take radians times 180 over pi. This will reverse it. We're going to get degrees. So for example, we're going to convert pi over 4 radians, 2 degrees. So take our radians, multiply by 180 over pi. We'll get 180 pi over pi times 4, 4 pi. Our pi's are going to cancel. We're left with 180 divided by 4, and that happens to be 45 degrees. And that's going to be your answer. Questions about that? All right. So one last thing I want to mention in this section, I'll just see here. So a counterclockwise rotation. So this is counterclockwise. That means we're going to be doing this. This is a positive angle. So that's going to be a theta greater than 0. Now, if we go clockwise, or in this kind of direction for the rotation, we get a negative angle. So there's the initial, here's the terminal. We're going to go in this direction. This is a theta less than 0. So questions about that? All right. So the last point I want to mention in angles is where you have multiple rotations, or what we might call coterminal. I'm just going to give an example of what it looks like. So a full rotation is 2 pi radians, or about 6.28 radiuses or radii. That'll give you a full rotation for any circle. So let's say we have this. So we have theta is pi over 4. So let me keep this angle. And let's say we have another one. But this one goes around once and then stops. So theta will be 2 pi plus pi over 4. And let's see, which will be 9 pi over 4. So what this means is that the terminal side for both these angles, for pi over 4 and for 9 pi over 4, the terminal sides of these angles overlap. So we say these are coterminal. So any questions about that? So we're going to look now at basic trig functions. So again, r is going to be the radius on this circle. And to find r, well, we can take this triangle. There's a height of y and a base of x. So r is x squared plus y squared, and then take the square root. So that's how you come up with r. So this is going to be our angle theta. And this is going to be true regardless of the triangle you come up with, or the triangles in this quadrant, this quadrant, this quadrant, or this quadrant. This is what sine, cosine, tangent, cosecant, secant, cotangent are going to be. The sine of theta is y over r. Cosine of theta, x over r. Tangent of theta, y over x. Cosecant theta, r over y. So we flip it. Secant theta, again, we're going to flip it. It's r over x. then the tangent of theta, oh, sorry, cotangent is x over y. So questions about this? All right. So let me do an example. So r will be the square root, and this is going to be x is 4, y is 3. So r is going to be x squared plus y squared, or 16 plus 9, or it's going to be 5. So if we want, say, the sine of theta, well, sine theta, that's y over r, which would be 3 over 5. And that's it. Cotangent of theta, this is x over y, or 4 over 3. And that's basically how you work with your trig functions. Questions about that? All right. So part of this is we end up doing what's called the unit circle. And this is when the radius has a value of 1. So the consequence, sine of theta, which is y over r, becomes just y. Cosine of theta, which is x over r, becomes just x. So that means on the unit circle, any point on that unit circle, the x and the y, well, this will be the same value as cosine theta, same as sine theta. So x is cosine theta, y is going to be sine theta. So that's how the unit circle is going to work. Now, with the unit circle, we have some canonical functions, and I can post a unit circle that you can use. I can put one up on the Blackboard website. Let's see. Oh, I got 10 minutes. Just watching the clock. So we have some basic triangles. So the first one now again, this is a circle, this is a triangle you can put inside the unit circle. This is the radius of the unit circle, and this would be the x-axis. This here is rad 3 over 2, and this here is 1/2. So this is going to give us a coordinate of rad 3 over 2, 1/2 for x and y. So there's a height of 1/2, a distance from the origin of rad 3 over 2, and so it gives a coordinate of rad 3 over 2, 1/2. So this tells us that the sine of 30 degrees is 1/2, and the cosine of 30 degrees is rad 3 over 2. I'll draw the next triangle so it's inside the circle, so it makes a little more sense. So it's on some kind of a Cartesian plane. Questions about this? All right. So yeah, I'll put this next one inside the circle. One, rad 2 over 2. Rad 2 over 2. So you get an xy coordinate. Rad 2 over 2. Rad 2 over 2. That's 90 degrees. So these here are 45 degrees and 45 degrees. So what this says is the cosine of 45 degrees is rad 2 over 2, and the sine of 45 degrees, the y coordinate, is also rad 2 over 2. So questions about that? All right. So there's one more. This is that original triangle, just tipped over is what it is. And we have a height of rad 3 over 2. We have a width here of 1/2, or a base of 1/2. So that means 1/2 rad 3 over 2 is the coordinate of the point on the unit circle. So what this says is that the cosine of 60 degrees is 1/2, or that x coordinate. The sine of 60 degrees is rad 3 over 2, the y coordinate. And so that's our unit circle. Now, that's not the whole thing. What we're going to be doing is we're going to be expanding on this. You can take the points here, 0 degrees, 30 degrees, 45 degrees, 60 degrees. You can reflect them to this side, then reflect them to here, and then reflect them to here. And that gives you the full unit circle. And again, I can post one of those on the Blackboard webpage. Last thing I do want to mention, and it's something from the beginning of this section on angles, or near the beginning, really the functions part. And this is our R, again, the radius on the circle. So we had that the cosine of theta was x over r. So you can solve for x, and then you're going to get r cosine theta is equal to x. Likewise, sine of theta is y over r. Solve for y. R sine theta is equal to y. And I think I better stop there. So what's left in this section, we have the periodicity of the trig functions. In other words, we're just going to kind of graph them and look at the periods. We have the trig identities. I'm just going to list those, and I might post those on the Blackboard page as well. Some formulas for solving triangles. This is the Pythagorean theorem, the law of cosines, and the law of sines. Some special identities are going to be relevant in the next chapter. And then finally, how do you graph trig functions using all the transformations like stretching, horizontal compressing, shifting that we just covered in section 1.2. So what's going to probably happen on Monday? We'll finish section 1.3, and I bet we can finish section 1.4 as well. That's the graphing section. That's not too bad. That goes by pretty quickly. It's how to use a graphing calculator. So we should be caught up by Monday. And that should will leave us 2 more sections for chapter 1, and that's going to be it. So if you have any questions on the homework, please let me know. I love answering math questions, and I'm checking my messages regularly. So if anything comes up, give me a holler. Other than that, have a wonderful day, and I'll see you next week, if I don't hear from you sooner.